So in this section, we're going to be going through the preferred structure of lipid aggregates. So previously, we took a look at what kind of structures could be formed. Now we really want to dig deep and take a look at spherical micelles, inverted micelles, and the interactions between lipid molecules. So we're going to go through a more thorough mathematical analysis of all the different types of structures that are preferred. So in this section, we want to cover the preferred structure of lipid aggregates. And similar to what we did before, we have to come up with a physical representation of what a lipid actually looks like. So we're going to try and use different shapes to model these lipids. So I want to first define the parameters that we can use by drawing a quick sketch. So the idea is to model a lipid or amphiphile using a convenient shape. So if I have a lipid that looks like this, then it kind of makes sense that it has almost a cone shape. So maybe I can have cone like this to use as a good model. So then here, we've expanded it to something along these lines. There's some sort of radius r, it's going to be at a certain height, LC, so this is approximately going to be labeled as L max. So you can use either one. Some textbooks use LC for when it reaches the critical micelle concentration, or essentially when it's at its optimal length. Then this is the maximum tail length. Then you have V representing the volume of each tail. So V is the volume occupied by each tail. Oops. You have L max being the maximum tail length. You have R being the radius of head group. I also want to introduce a term that is just A, and that is commonly represented by little a naught, which is the optimal or preferred head group area. So with all of that, we'll be able to model. We can model and predict the different curvatures of micelles and aggregate structures. So essentially we'll be looking at cones quite a bit. Let's now take a look at spherical micelles. So I want to try and model an actual micelle. So I'm going to first draw a micelle, and let's have something that looks like this. And one of the things we want to label in here is the center of the micelle. So that would be our origin point. So this is smack in the middle. And you have this being your radius R. When I model this, I can convert it into something a little bit more basic. So instead of using an actual graphical representation of a micelle, we'll just use cones. So this should be able to give me maybe not. I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe drew this too much. I obviously can't draw right now. So I have this. And this. This should be really in the middle. That. We kind of want them all to fit together nicely. Like that. So here, I now have what's called a model by cones to represent each lipid. So we'll definitely need a way to try and quantify this. So let's call M the preferred N-mer configuration of a micelle. So the preferred N-mer configuration of a micelle, another way to explain it is when the first micelle is formed. So then we define M to be equal to 4 pi capital R squared over A naught, and that's equal to 4 pi capital R cubed over 3 times V tail. So the other way you can write this is M, because we have this component being equal to V equals 4 pi R cubed over 3. We have the volume of the sphere, so therefore you can actually rewrite the whole thing as V over V tail. But then if you wanted to determine the value of R, then you would have R is equal to 3 times V tail divided by A naught. And that should be usually less than L max. So now we want to think about why the radius here needs to be less than the maximum tail length. If we think about the maximum tail length, it's going to be the length of the lipid tail that is fully stretched. But in reality, when it condenses into a micelle, the tails are probably going to be a little bit squished or compressed. So therefore, the radius of your micelle should be less than the maximum length of your tail. So we're going to go through that analysis in the next slide. So the first thing is for R is greater than L max. So I want to do a side-by-side comparison of what happens if we do have a radius that's greater than L max, and another one for what happens when R is less than L max. So when R is greater than L max, what this is saying is, I'm just going to draw one lipid first. So let's say I have a lipid here. This is essentially my L max. What this is saying is we're going to end up with a radius that's much longer, or just longer than L max. So what kind of shape will we even get from this? We're going to get a shape that looks like this. But the better way to draw this would be along the lines of this, and I'll erase that after. Okay, so that would be our shape, with the center being here. This would satisfy the requirement for R being greater than L max. So does this make sense? Probably not so much. It seems like no matter what, there's going to be some sort of hydrophilic core in here exposed to the lipid tails, which is something that is highly unfavorable. So this would be considered an unfavorable conformation. Now, what happens when R is less than LC? It's pretty much what you've seen before. You now have a lipid like this. This is L max. And we're basically saying that R is just going to be a small segment of that. So what this looks like something like this. The center is right here. There is no hydrophilic core. All of the spaces in between these are pretty tightly knit so that no water can get through, so it almost acts like a barrier. So this would be called biologically favorable and biologically relevant. So whenever we're performing studies on micelles, we always want to assume that the radius of the micelle that we calculate is going to be less than the maximum length of the tail of an individual lipid. So what other things can we try and analyze here? We can actually have something along the lines of this. So over here I have a term where for spherical micelles you have an R value that's going to be in between 0 and 1/3. So this would be for spherical micelles. And spherical micelles are essentially these ones, so I'll call this a spherical micelle. If you have a value of V tail over A naught L max between 1/3 and 1/2, you get what's called a cylindrical micelle. And essentially what's happening here is you have more of an oblong shape where the micelles are going to be more like stacked on top of each other. And then if you have 1/2 to 1, then you end up with bilayers, because that means that bending is not preferable to that degree. So these are just certain values, or common values that, once again, have been derived from different types of models and have been used regularly for theoretical studies of lipid self-assembly. So you can take a look at each of these models too to see whether they can be improved, whether it's good, and to see what's been done with those. So now we went from 0 to 1/3, and then from 1/3 to 1/2, and 1/2 to 1. So what happens if it's greater than 1? So that's going to be our next slide. When V tail is greater than 1, we get what's called an inverted micelle. Oops, not V tail. V tail over A naught L max. So what an inverted micelle is actually, it's a micelle still, but it has a very long tail structure. So the packing pattern will favor the tail end portion of the lipid or the amphiphyll. So this means we get something like this. And this works because we can assume your lipid is actually taking up more space than the head itself. So this is just a quick example, and we want to say that the lipid head could technically be very small like this, and you could have a tail that goes like that. So you have a very kinky tail. The wider the tail and the smaller the head, the greater the ratio between the two, the more of a chance that you'll get an inverted micelle. So then if we want to take a look at typical values in a living cell, I briefly want to mention that in a living cell, these common parameters have been defined. So LC, or L max, is equal to 0.126 nanometers per carbon atom in the tail. So then you would have 0.126 times the number of carbons. You have V tail being approximately equal to 26.9 times the number of carbons, so NC once again, times 10 to the negative 3 nanometers cubed. So then with all of this, you can say V tail over L max oops, sorry, I should not have written this one down here. That would have been like L max many times over. So V tail over L max is equal to 0.21 nanometers squared for a single-tailed lipid that's going to turn into a micelle. You have 0.42 nanometers squared for a phospholipid with two tails, and that's going to create a bilayer. So you can kind of see that these are almost doubled. If you have double the V tail over L max, then you're going to move towards the formation of a bilayer because you've surpassed a certain threshold. Next, we want to take a look at interactions between lipids. So for this, we want to draw a graph, and this is just something that I grabbed from an article to explain what happens. We have A going here, and that is basically our head group area. And then you have free energy here. There are two curves that we plot. One is like this. We give it a label of gamma A, and we say gamma is the interfacial free energy per area. We also have another curve that looks like this. We label it K divided by A, where K is the strength of repulsion. Then you have something like this, which we call mu n naught, which is defined as gamma A plus K over A. So one of the things we should mention here is that gamma and K are constants that we'll have. A is the area occupied by each molecule. So head group area, or area occupied by each molecule. And within all of this, after you graph all three of them, you should be able to come to an intersecting line across all three graphs and state that this is A naught, or the preferred head group area. So once you know the interaction between different lipids, you'll be able to plot this graph, which I'm not showing how to in the course. It's just to explain how one can use the different terms that we've learned to try and plot something and be able to figure out a preferred head group area that you can plug into your model, and it can spit out the preferred conformation of your lipids and its most likely or most favorable aggregate structure. Next, we also took a look at bending of things in DNA. So we want to take a look at bending of the bilayer or the elastic sheet in this case. So I'm going to say similar to the bending of DNA. So in this case, we're going to have a bilayer. So we have this as our bilayer. Oops. And if I want to bend it, remember we have something along these lines. We're going to consider this to be our middle or central axis, or the midplane. We also have this being L0 plus delta L. So basically this would originally be a length of L, but now the top part has been stretched or changed by a distance of delta L, and the bottom part has been compressed by delta L. And then put this together. This can be labeled as theta. This would be R, and this would be D0. So when we're bending the bilayer or the elastic sheet, we can use the exact same analysis from DNA and apply it here. So I won't go through that again because the math is pretty much the same. You can also get the bending modulus of this, similar to how we did it for DNA as well. So just as a recap of this, I would say potentially for the bonus modeling project, you could apply or modify the equations for DNA modeling to this case to see if you'll be able to figure out an actual value for different types of bends for a lipid bilayer. So now the last things I want to go through are something called spontaneous curvature. So with spontaneous curvature, there are actually 4 options. Or basically 4 cases. You can have the curvature represented as kappa. You can say kappa is less than 0. You can say kappa is greater than 0. You can say kappa is equal to 0. or basically kappa can be anything else. So if it's not 0, we can make some general assumptions from that as well. So looking at 4 of these different cases, when your curvature is less than 0, then what happens is you have something called bulky tails. That means my curvature is going to be inverted. Because it's no longer positive, it's going to be inverted, so I end up with an inverted micelle. So this would be something along the lines of that. Now, if I have kappa being greater than 0, then it means that there's really high curvature. We call that bulky heads. So this would essentially mean you have a normal micelle. So going like this, you'd actually have something like that. So basically it's saying between the two of them, here you have bulky tails because your cone shape is going to look like this. Here you have bulky heads because your cone shape is now going to, I don't know why that's shifted over so much. Something like that. So fully inverted between the two of them. Now, what happens when kappa is equal to 0? So when kappa is equal to 0, it means that you're going to end up with some sort of symmetry. So that means I might have something like this. And this. So we would say kappa is equal to 0 if everything is symmetrical. Then for values where everything is not symmetrical, you can actually have this from the outer side. You can have a cylindrical shape. And you can have a curved shape here. And in this case, there is no symmetry to cancel things out. So those are the 4 different ways of representing spontaneous curvature. We're going to go into a lot more detail about these curvatures in the next section. So keep in mind for this course only, or for just this course itself, you would just need to know how to graphically explain these values. You won't have to know how to calculate them because it does get very complicated if you do want to do a full analysis of lipid curvature. So I do go through that in the next section, which you're more than welcome to watch and learn from and potentially use as your modeling project. But for this, it's specifically just a graphical representation of what types of curvature can occur.